welcome to another module in this massive open online course. So, we are looking at the sampling of analog signals. In this module, let us start looking at also the reconstruction aspect, that is from the samples of the sampled signal, how can we reconstruct the original signal, alright. So, let us look at, so we are looking at sampling. Let us also start looking at reconstruction, that is how do you reconstruct that is if you want to reconstruct the original samples, how do you reconstruct the original signal from the sample. So, we want to look at the reconstruction aspect. So, sampling and reconstruction. Now, we have already seen that the sampled signal, if MT is the original signal, this is your original signal. Now, the sampled signal M delta t is given by multiplying this by an impulse train, that is MT times summation n equal to minus infinity to infinity delta t minus NTS. This is your impulse train, correct. So, this is your impulse train, which is a series of impulses at every multiple of the sampling time interval Ts, okay, where sampling frequency Fs equals 1 over Ts, okay. Fs is the sampling frequency, this is our sampling frequency. And now, we are multiplying MT by this impulse train, that is MT times summation n equal to minus infinity to infinity delta t minus NTS, and that each impulse at NTS, right, picks the value of the original signal M at NTS. So, we have from this impulse sampling, what we are going to get is your M delta t equals summation n equal to minus infinity to infinity M of NTS times delta t minus NTS, that is impulse at NTS scaled by the function MTS. So, impulse, so what is the summation of impulses at NTS scaled by impulse at NTS scaled by the function, that is M at function at NTS. Now, also when we looked at the frequency response, we looked at the Fourier transform of this, that is if M delta t has a Fourier transform M delta f, we said that M delta f is basically M of f convolved with, since in the time domain we are multiplying, in the frequency domain we have to convolve with the frequency response of the impulse train, and the frequency Fourier transform of the impulse train we have already seen is summation is Fs summation n equal to minus infinity to infinity delta f minus nfs, which is equal to Fs summation n equal to minus infinity to infinity m of f minus Fs. So, this is your M delta f, this is the Fourier transform of the sampled function, okay. This is the Fourier transform of your sampled function. or basically the spectrum of the sampled function m delta t, and if you write this, what you will see is that this is Fs. So, Fs is a scaling factor, and Mf, the original spectrum Mf shifted to each NFS, that is Mf minus NFS, shifted to every multiple of the sampling frequency and the sum of all these spectral copies. So, what you have is very interesting. You have Fs times m of f plus Fs times m of, well, f minus Fs plus Fs times m of f minus 2Fs plus so on, plus also Fs, that is this copy shifted to minus Fs, Fs m of f plus Fs, Fs m of f plus Fs plus Fs m of f plus 2 Fs, that is copy shifted to minus 2, and so on. Alright. So, this is basically the sum of spectral copies, shifted to of MF shifted to each NFS, where n shifted to each NFS, where n is any integer, Fs is the sampling frequency. So, therefore, this is a very beautiful frequency domain interpretation. If you look at it in the frequency domain, what we have is you have your original spectrum. If you have your original spectrum, that is MF, which is has maximum frequency FM, let us say, minimum frequency, that is from minus FM to FM, that is its support, or where it is non-zero is from minus FM to FM, the maximum frequency is FM, this is the maximum frequency. And therefore, now what you are doing is basically you have Fs times Mf. So, the sampled signal m delta f will be, well, Fs times Mf. So, this is f of m, Fm minus Fm. So, this is Fs times Mf. Then you have another copy at Fs shifted by Fs, which can be, this is Fs. So, naturally this point is going to be Fs minus Fm, this point is going to be Fs plus Fm, this is your Fs times m of f minus Fs, so on. You are going to have copies Fs m of f minus 2Fs, copy at 2Fs, and also similarly you can have a copy at, that is, if this is your minus Fs, and this is minus Fs. So, naturally this point is going to be minus Fs plus Fm, this point is going to be minus Fs minus Fm, and now you can see there is an overlap here, there is a possibility of overlap of spectral copies and this overlap of spectral copies, this leads to distortion. That is what we said, overlap of spectral copies, overlap leads to distortion. Okay. Distortion means that the sampled spectrum is a distorted version of the original spectrum, that is m delta f, that is sampled spectrum. What does this imply? Sampled spectrum or I should not say sampled spectrum, rather I should say spectrum of sampled signal. We are not sampling the spectrum, but rather the spectrum of sampled signal. Spectrum of sample signal is a distorted version of the original spectrum, and this distortion is termed as, this is very important, this distortion is termed as aliasing. We have said that this distortion is termed as aliasing, that is these different spectral copies alias. Okay, and the condition for aliasing, remember we have also derived the condition for aliasing. Aliasing occurs when fs minus fm is less than fs. So, aliasing occurs when if fs minus fm is less than fm, that implies fs less than 2 fm, that is sampling frequency is less than twice the maximum frequency. So, this is the condition for aliasing. Therefore, to avoid aliasing we need fs greater than or equal to 2 fm, that is the minimum sampling frequency. To avoid aliasing or the distortion caused by aliasing is fs greater than or equal to avoid aliasing we need fs greater than or equal to 2 fm, where fm is the maximum frequency, and this is known as the Nyquist criterion. This is known as the Nyquist sampling theorem, or this is known as the Nyquist. This is known as the Nyquist criterion. And remember, when fs is greater than fm, what is going to happen? This is your original spectrum. Let us say this is your original spectrum mf between minus fm and fm. You are sampling at sampling frequency greater than fs, then you are going to have this original spectrum first scaled by, well, scaled by fs. So, this is your copy fs into mf. Now, if fs is greater than fm, you are going to have another copy over here. So, this is fs. So, this is fm, this point is fs minus fm, this point is fs plus fm. Similarly, if you look at this over here, so this is fs mf minus fs. Similarly, and then you will have various components fs mf minus 2 fs and so on. Similarly, here you will have at minus fs, this is your minus fs plus fm, this is your minus fs minus fm, and now realize there is no overlap or no aliasing if fs greater than or equal to fs is greater than or equal to 2 2 FM. So, there is no overlap or aliasing is if Fs is greater than or equal to 2 FM, and now there is no distortion. Alright, since the sampling frequency is greater than or equal to twice the maximum frequency, there is no distortion. Now, you can see that we can reconstruct the original message signal from this sample spectrum, and the way to do that is by filtering this copy, the copy of the spectrum which is intact at the frequency 0, that is we have Fs times Mf which is intact in the baseband, that is which is intact at which is centered around the 0 frequency. I can extract that by low pass filtering this with an ideal low pass filter. Okay. So, now I can extract this. Now, this is, remember, this is Fs, this is 0. So, this is your Fs by 2, Fs over 2, sampling frequency by 2, this is your sampling frequency by 2. Now, I can extract this by low pass filtering this, by low pass filtering this. You can clearly see if I have low pass filter with cutoff at Fs by 2, and there is a scaling factor of Fs. So, this has to be 1 over Fs, the height of this has to be 1 over Fs equal to Ts. So, now I can reconstruct the original. So, now we realize something interesting. I can reconstruct if there is no aliasing. Remember, if there is no aliasing, that is an important condition. If there is no aliasing, reconstruct or original message signal or MT can be reconstructed, that is original signal can be reconstructed by passing m delta t through a low pass filter with cutoff frequency equals Fs by 2. The cutoff frequency of the low pass filter is Fs by 2, that is it is 1 if f magnitude f is less than Fs by 2 and 0 otherwise, and also there is a scaling of Fs. So, to invert that you have to multiply by 1 over Fs, therefore, and so cutoff frequency is Fs by 2 and the height of the response is 1 over Fs, that is Ts, and frequency and height and frequency response magnitude equals 1 over Fs equals Ts. So, the filter looks like this. Basically, I have my filter, okay, and now I have a low pass filter with cutoff equals Fs by 2. So, this is Fs by 2, this is minus Fs by 2, the height of this is 1 over Fs equals Ts. Okay. So, this is my reconstruction low pass filter, low pass filter for this is my low pass filter for reconstruction. Let us term this as h of t. So, this is h of f, which is a response of, let us say, the impulse response is h of t. So, we have h of f, the response is basically, it is easy to write this down, this is h of f which is equal to 1 or basically Ts if f magnitude of f is less than or equal to Fs by 2, where Fs is the sampling frequency and this is 0 and this is 0 otherwise. Okay. So, this is basically the low pass filter, that the LPF for the low pass filter that we want to employ for reconstruction, okay, which is magnitude Ts if f is less than or equal to magnitude f is less than or equal to Fs by 2, 0 otherwise. Okay. And now this low pass filter, you can find out the impulse response of this, that is a time domain impulse response, and the impulse response of this we already know, this is a pulse remember if it is if the signal is a pulse in the time domain, then in the frequency domain it is a sinc. And if you apply duality, if it is a pulse in the frequency domain, naturally the impulse response or the response in the time domain must be a sinc function, and the response of this in the sinc domain, that can be seen as follows, that is that can be seen as follows. From duality, this can be easily obtained as this is sinc of the corresponding h of t equals sinc of fs comma sinc of fst. Okay. So, this is basically the sinc of fst, that is a sinc function in the time domain. This is where sinc of x, remember sinc of x equals sin pi x by pi x. So, sinc of fst h of t equals sinc of fst equals sin of pi fst divided by pi fst, where fs is the sampling frequency. Okay. So, this is the sinc function in the time domain, and we can derive this, and this can be derived by, let us note that this can be derived by duality. And this can be derived by duality. Okay. So, this can be derived using duality. Okay. And therefore, what we have, this can be derived by using the principle of duality, we know that the principle of duality. Okay. Now, therefore, we have this signal MT. So, what we have to do to reconstruct the signal for reconstruction. Now, let us highlight that procedure for reconstruction. We take our sampled signal m delta t, pass it through the system with impulse response h t, and that gives this. So, m delta t convolved with h of t, that gives back our original signal m t when there is no aliasing, right, because we are low pass filtering to extract the component at 0 frequency. There is a component between minus fm and fm, which is simply a replica of the spectrum of the original signal mt scaled by fs. So, we are multiplying by the low pass filter, which is response which has a cutoff frequency fs by 2, and obviously to invert for that scaling or to account for that scaling, we are scaling this by 1 over fs or basically ts. Okay, that gives us back the original spectrum. It gives us back the original spectrum in the frequency domain. In the time domain, naturally in the frequency domain we are multiplying, so in the time domain it is basically a convolution. Okay, and that can be expressed as follows. Now, if you look at that, our m delta t, the sampled signal, is summation n equal to minus infinity to infinity m of nts delta t minus nts. Now, I have to take m delta t and I have to convolve with sinc of t fs, that is sinc of fst. Remember, this is our reconstruction filter, sinc of t fs or basically sinc of fst, and therefore, what we can see is m of t equals m delta t convolved with sinc of fst, which is equal to basically, now we have our m delta t. Also, I can write this as convolution is commutative. So, I can write this as sinc of fst convolved with, I can interchange m delta and sinc. So, this is sinc of fst convolved with, well, m delta t we have already seen, that is n equal to minus infinity to infinity m of nts into delta t minus nts, which is basically equal to, which equals, well, Fs taking the sinc inside, that is n equal to minus infinity to infinity, sinc of Fst convolved with delta t minus nts. Now, a function convolved with delta t minus nts, the function is simply shifted to nts. So, that is Fs shifted by nts. So, that is n equal to minus infinity to infinity sinc of Fs of t minus nts, where we are once again using the property, that is function x t convolved with delta t minus t naught is simply x of t minus t naught, that is x of t shifted by t naught. So, sinc of Fs t convolved by delta t minus nts is simply sinc of Fs t minus nts. And now you will realize that Fs into nts is 1, because Fs is the sampling frequency, Fs into Ts, because Ts is 1 over Fs. So, Fs into Ts equals 1. So, if I use that principle over here, what I get is summation n equal to minus infinity to infinity Fs sinc of Fst minus Fs into nts, that is simply n, and that is the original reconstructed signal. That is how we can reconstruct the original signal by passing it through the sinc filter, or this is basically a filter whose response is basically, this will be your I am sorry, I am missing the MNTS, there has to be an MNTS, M of NTS, and this is also, there will be M of NTS. So, what we are doing is basically we are shifting, correct, we are shifting, of course, there is no Fs, there is no Fs, because this is simply your MNTS into delta t minus Ts. So, this is simply M of NTS. So, anyway, so what we are doing is basically we are taking each sinc Fs, shifting it to NTS, that is shifting sinc of Fst to each NTS. To each NTS, scaling by MNTS, scaling by MNTS followed by the sum. So, what we have essentially is basically, and remember sinc of FNTS, sinc of FST, the zeros, this is equal to basically sine of pi FST divided by pi FST. So, this is zeros are at, the zeros of this are at integer multiples, that is at k times Ts, because this is at every k times Ts, this is sine of pi Fs k times Ts divided by pi Fs k times Ts, Fs into Ts is 1. So, this is sine of k pi divided by k pi, which is 0. So, the zeros are at basically k times Ts, that is at every integer multiples of Ts. So, therefore, now what you are doing is essentially, if you can look at this, you have your sampled signal m delta t, which consists of impulses, correct. So, this is your m of, this is your sample, which is basically your m of NTS. So, let us say n equal to 0. So, this is your sample, which is m of Ts, this is your sample, which is m of 2 Ts, and so on, and this is your sample, which is m of minus Ts, this is your sample which is m of minus 2 Ts and so on. Now, what you are doing, you are shifting the sinc to Ts, scaling it by m of n Ts or m of 0, and then you are superimposing this sinc. Okay. So, you are taking the sinc, scaling it by m of 0, sinc amplitude at 0 is 1. So, you are scaling it by m of 0. So, now and remember that is one sinc whose zeros are at, remember this. So, this is Ts, this is 0, this is 2 Ts, okay, these are 0. So, this is 0, Ts, 2 Ts, minus Ts, minus 2 Ts, and now when you scale it by m0, remember the zeros are still at Ts, 2 Ts and so on. So, what you are getting is the sinc which is like this, that is the zeros are at basically the various samples. And now then you are taking a second sinc, scaling by m of Ts, and the zeros of this sinc will again be at, this is an important property of the zeros of this, which is basically scaled by 2 Ts are going to be at scaled at Ts is going to be at 2 Ts 0 and so on. And then you are taking another sinc, shifting it to minus Ts, and the zeros of this are going to be at these are going to be at, well, minus Ts is going to have zeros and so on. And what you are observing is basically from this figure, what you can observe is basically the reconstruction is nothing but a sum of shifted sincs. You are taking each sinc function, sinc of fst, shifting it to n times Ts and scaling it by the value of the sample, that is m of n times Ts. Okay, scaling it by the sample m of n times Ts, and then basically summing of all these shifted scaled sinc copies. And the interesting properties are the zeros, that is wherever you are scaling it by n of Ts, wherever you are shifting the sinc, scaling it by m of n Ts, shifting it to n of Ts and scaling it by m of n Ts, the zeros of this sinc coincide with basically the other samples. So, it is not affecting the other samples. So, the reconstruction at the samples exactly is unaffected, and that is true because if you have to reconstruct the original signal back, then we know the values at the samples, they are simply m of 0, m of Ts, m of n Ts and so on, alright. So, the reconstruction is not affecting the samples at the locations, alright, and this is an interpolation, alright. What we are doing essentially, we have these samples and we are interpolating these samples to create the original signal MT, and this is interpolation using the sinc filter. So, what we are doing is literally basically we are interpolating using the sinc filter. This process is basically we are interpolating the samples. We are interpolating the samples using the sinc filter. And what is a reconstruction? If you look at this relation over here, that is m of t equals summation n equal to minus infinity to infinity m of n Ts sinc of f Ts minus NTS, that is this is basically shift, that is basically shift sinc FTS to each NTS scale by MNTS and sum all shifted copies of this function sinc of this is sinc of FST, sinc of FST, sinc of FST minus FST minus NTS, correct, sinc of FST minus NTS. So, you are shifting this sinc of FST scaling by M of NTS and sum of all shifted copies of the function sinc of FST, and that is what you are doing, and this is basically your sinc interpolation. Or basically interpolation, sinc is the interpolation filter. So, interpolation filter is sinc function, has a sinc response basically. In the time domain. This is the interpolation filter. The sinc function sinc of FST is nothing but the response of the interpolation filter. Alright. So, basically what we have illustrated is how to reconstruct the original signal, which is very simple. When we do not have aliasing, when Fs is greater than 2 FM, then we can low pass filter it with cutoff frequency Fs by 2, and to invert the scaling we can have the height of the filter or the magnitude response of the filter is 1 over Fs, that is Ts. Alright, the corresponding response in the time domain is sinc FST. So, we are passing the sampled signal through this filter with response sinc of FST, we are able to interpolate the samples, alright, interpolate the samples of the sampled signal and basically reconstruct the original message signal MT without any distortion, since there is no aliasing. Alright. So, that concludes the reconstruction aspect of the original signal. Alright. So, we will stop here and look at other aspects in the subsequent modules. Thank you.